Jinich. I'm from the School Music Lab, which is a computational quantum chemistry lab. Does it sound right? Can you hear me? Yeah. And I'll talk to you about estimating the thermodynamics, the Gibbs reaction energies of metabolic reactions. And so we know a lot about metabolism, and you've probably all seen these maps, but maybe you haven't seen this particular map of metabolism. It's relatively new. It's from Sigma Aldrich. You can navigate different pathways. It's interactive. And it highlights the amazing, vast amount of knowledge that our ancestor biochemists have compiled over decades, figuring out each specific reactions and connecting the network. It's impressive. And whenever I see the network, I'm not simply impressed. But there's another aspect of metabolism which there are things that we don't know. In particular, there are many gaps in the data that we have for the thermodynamics or the Gibbs reaction energies of metabolic reactions. And so here's another representation of a sub-network of metabolism. This is lysine, serine, and threonine metabolism according to Kane. And I'm highlighting in red steps for which no one has ever measured the equilibrium constant of that particular reaction. So no one has done the experiment to measure concentrations at their equilibrium. So you can see there's a lot of red in this diagram. And it turns out that we only have experimental standard Gibbs reaction energies for about 10% of known metabolic reactions. That's an estimate. And most of them are compiled in a beautiful database in NIST, Thermodynamics of Enzyme Catalyzed Reactions database. An amazing job in compiling from literature from the 60s, known equilibrium constants. So this is a very different situation from what you might see in other fields of science or engineering. So for example, in experimental electrochemistry, you will run into books like this edited by Alan Bard, which are like a Bible of reduction potentials of different compounds. So that contrasts very much to what we have in metabolism. So why would we be interested in obtaining accurate predictions of the missing Gibbs reaction energies of metabolic reactions? So before I jump into it, just a brief primer. Just to remind you, the Gibbs reaction energy doesn't depend on the enzyme, it just depends on the substrates and the products. It's related to the equilibrium constant by this very simple, beautiful relation. And although it's related to the equilibrium constant, you can get non-equilibrium Gibbs energies from it, not by adding if the reaction is out of equilibrium, you can add the concentration-dependent terms and you get the Gibbs reaction energy out of equilibrium. So why is that useful? It's useful in the context of metabolic engineering. So for example, this is a synthetic pathway that some collaborators in Germany are trying to build, in which E. coli will fix formate and convert it into biomass, and it will pass through the lysine cleavage system, an amazing step in metabolism. But in order, before building it, trying to build it in E. coli, you have to make sure that the thermodynamics are favorable. Otherwise, it will never work. So that's one example of how it's useful in synthetic biology, in metabolic engineering. Whoa, what just happened? Let me scroll back to my presentation. No. Okay. Does this count in my time, or can I? Thank you. This had never happened before. Alright, let's try this. Here we are, thank you. Okay. One second. All right, another less appreciated aspect is that thermodynamics is linked to kinetics in a very amazing way. So people might be familiar with this expression on the top. It's like Michaelis Menten kinetics for unimolecular reversible reaction. But there's a beautiful result called the Holley Relationship, which lets you rewrite that expression as a product of three terms, one of which depends on the Gibbs reaction energy. And you can see this beautiful decomposition in the lab Moore's paper, which I cite here. So there's a link between thermodynamics and kinetics. And so why quantum chemistry? So current approaches center around a technique that's machine learning based, which is called group attribution method. It's amazing that they've done a lot of progress, but it has its limitations. It relies on fitting to experimental data. It doesn't account for interactions between functional groups because there's not enough data to fit against. But and it's hard to, although we can measure the equilibrium constants, it's hard to measure them in a high throughput manner. Imagine measuring thousands of equilibrium constants systematically. Although there are very exciting efforts in our environments lab at Max Planck to do this. So the focus of my project is to estimate the Gibbs reaction energies, standard Gibbs reaction energies, using a quantum chemistry approach, and ideally want to be as close to 1 kcal accuracy as possible. So how do we go about this? In general, you have a reaction like this is central reaction in glycolysis, like hydroxyacid phosphate to glyceraldehyde phosphate. And you start by one approach would be to model each metabolite as an ensemble of coordination states. So here, I have one of the involved metabolites. You can notice the phosphate doesn't have any protons. But if I'm at pH 7, I might also want to take into account this other coordination state, which does have a proton, different charge. And they're at equilibrium pH, so you might want to take them both into account. And then you might want to take into account all the possible different geometries. So one approach is to start out with a bunch of different conformers. This is for a given coordination state, a bunch of different initial geometries, which will ideally let you explore different portions of the potential energy surface of this molecule. And then I won't go into details, but you have to probably account for waters, and there are different ways to do that in quantum chemistry. There are implicit formation models where you explicitly put water molecules around it, or you do a mixture of the two, or you do these more sophisticated part quantum, part classical waters. And then you put these to quantum chemical simulations, which, if you're not familiar, it is kind of simple. You start with a geometry, you minimize it to find a minimal energy conformation, then you take an accurate value of the energy of that conformation, and then you try to model the vibrations by doing harmonic analysis to get the vibrational contributions to the free energy. But before you jump into that, what I realized at some point in the project is that you have to make many decisions. And so this is a table showing the things that a quantum chemist has to decide before running a simulation. So if you're going to do electronic structure, you have to decide what theory you're going to use. Are you going to use density functional theory? Or are you going to use a wave function method like coupled clustering or molar plastic perturbation? If you're going to use DFT, you're going to have to choose a functional. Which one are you going to choose? There's a whole slew of functionals out there. You're going to have to choose a basis set to model your electrons, which thermodynamic framework, what I just explained, or you can do molecular dynamics, and the list goes on. How do you model water? Do you put explicit waters? How many do you put? Et cetera, et cetera, et cetera. You can imagine. So you enter your PhD, you have no idea how you're going to start, so you go ask an expert to read the literature, and the expert says, bam, this is the right way to do it, no? Use that basis set, use that functional, and that'll give you good formation energies. You ask the next expert, and the next expert disagrees, or you try it and it doesn't work, etc. And suddenly you realize that you're sitting in a space, in like a model chemistry space, like quantum chemistry has evolved under all these approximations, and there are tons of ways to do things. So what I've been playing around with lately is, oh, not again, please. Sorry about this. What I've realized lately, there we go, is that we're sitting in a model chemistry space. And that we need strategies and tools to explore this model chemistry space. It's too big for us to do it thoroughly, combinatorially, and we could use the help from the amazing field of machine learning. And so we set up a collaboration with the Ryan Adams group at Harvard, which is called Harvard Intelligent Probabilistic Systems Group. And they've been developing this awesome framework called Bayesian optimization. I'm not an expert in Bayesian optimization, but I'll tell you briefly what it means. It's a useful way for black box optimization problems where you want to optimize over some variable function, an objective function. And black box generally means you can observe the function, you can evaluate the function, but you cannot get the gradients, so you don't know, you can't do all these gradient-based strategies, and you might get some noise in the observations. And so what we've set up over the last months has been an automated infrastructure where the machine learning makes a decision on which choices to make out of all these possible. It generates the quantum chemistry input files, and it runs them in a cluster such as Exceed or a Harvard Odyssey cluster. It waits for the calculation, which can take from hours to days. It gets back the data, processes it, compares to the experimental gives reaction energies, and goes back and makes a new decision on different basis sets, functional, etc. It took us a while to set this up, but it's starting to work. Previously, we were using a thing called WetLab, which is a basic optimizer, but it was just sold with Twitter, so I can't use it anymore, which is sad. But which is good because it means it's a valuable tool for optimization. But we're switching over to other machine learning optimization tools, in particular Experiment, which is also from the Ryan group, and SMAC, which is exciting because it's supposed to be smarter about optimizing over non-continuous variables, which is what a lot of our variables look like. And so first I'll show you a few results. This is still exploratory of, I want to focus only on implicit models. So the first thing the experts will tell you is that you won't get anywhere very far if you don't put actual waters in your system, no? Because they need to interact with the charged solvents, etc. But I want to see what are the limits to implicit solvents. They're cheaper. How good can we do? And first thing I learned that it is difficult if you're treating charged solvent molecules. It's difficult to get accuracy. So what I'm showing you here is for a few test reactions, we ran a bunch of these parameter combinations, and I'm showing you the average accuracy grouped by different variables. So this is grouped by DFT functional. The main point is that it doesn't go beyond below 3. We want to get down to 1. No? But you try a bunch of different combinations of DFT functionals, of implicit solvent models, of basis sets, but you're not getting very far down in accuracy. No? So treating charged molecules with these implicit solvents is indeed challenging. However, I quickly learned that the Bayesian optimizer quickly started choosing to work not with charged solutes, but it quickly started protonating my molecules and decided to work with only fully protonated molecules, which you might argue is not physically what's going on at a given pH, but apparently works. So here's an example of a reaction that is very difficult to treat in the charged state with only implicit solvents. And bam, if you fully protonate the molecule and get the Gibbs energy of the fully protonated species, you get it down to below 1 pCal per mole on average. And okay, that's interesting. It might not be very kosher, but it's interesting. It's a practical way to get accurate things. So can we actually predict accurately a specific reaction which we might want to, that's missing data? And so the strategy we're doing is we're interested in this particular reaction. We find reactions in metabolism that are similar, have similar chemistry according to these EC value classes. So these are isomerizations which transfer a phosphate from one to the other. So you can look for all the similar reactions that have data, run your optimizer on those, see how it behaves, and then you're confident that you'll predict. And actually, I told you, we actually do have data for this one, and I can predict it with less than 1 pCal per mole accuracy. So it's a promising strategy. And it turns out if you do it on a larger test set, how does it work more globally? And I can see that I get same or better accuracy levels by implicitly solvating neutral molecules, which is less calculations and faster, as with the other more standard approach, which is mixing implicit waters on the charged molecules. And so this is data on about 100 reactions. I'm plotting the cumulative distribution function for the error. So the farther it moves this way, the better. But they're pretty overlaid, and one was much cheaper and much less calculations than the other. Whether I want to use it for actually predicting metabolism, it's not clear. We're still working on data on this, but quantum chemistry sometimes runs into trouble when dealing with large cofactor molecules which are ubiquitous in biology. NADH, NADP, NADPH, ATP, ADP. Those are big molecules and it might be hard to capture their formation energies accurately. But we are working on strategies where you can only fit a single parameter, which is the difference in Gibbs energies of these cofactors. Fit that parameter, do quantum chemistry on the other molecules, and potentially get accurate results. And we're working on basic optimization of a bigger subspace of the model chemistries, which includes explicit waters around the solvents. And that complicates things, so you have to figure out how to place it, how many to place, et cetera, et cetera. How am I doing on time? All right, so you can thank me. I'm going to finish fast. To summarize, techniques for machine learning, such as basic optimization, are an exciting, I think, a promising approach, and which hasn't been explored before, to optimize over the full space, combinatorial space of model chemistries. We're starting to get glimpses of reactions that we can predict with chemical accuracy using quantum chemical approaches. We find this interesting behavior where the Bayesian optimization decides to fully coordinate molecules as a practical way to get accurate results. There's a lot more work to do. And I'd like to thank the members of this group's lab at Harvard, Ryan Adams' lab at Harvard for machine learning, the Ron Milo lab at Weizmann Institute, who got me interested in the thermodynamics of metabolism in the first place, Aaron Barrett, who now has his own lab at Max Planck, and he's the one who's pushing forward, trying to measure in a high-throughput manner equilibrium constants so that we can compare. And our funding comes from the Science Ministry in Mexico and the Mexico Harvard Foundation. Thank you. Any questions?
So I have two questions. One is, in general, how close is delta G going to be in an in vivo situation to delta G as defined in some standard chemistry laboratory? I mean, I just don't know, typically how. And the second question, I guess, is when you go through this sort of machine learning, it sort of implies that you understand enough about, and you sort of said this, how to break up your reactions such that you can identify 10 reactions that you know and use as a training set, and then there are 10 similar ones that somehow should be useful with the same set of techniques that now you're going to use your method on. Because obviously the method is going to depend to some extent on what reactions you're using. So those are my two questions.
Yeah, I think it's a limitation of the experimental data, how accurately your in vitro delta G value corresponds to what's going inside the cell. And people work very hard on doing the buffer solution that's similar in ionic concentration in different ionic species to what they imagine. But that's a limitation. I think there are techniques to indirectly measure there's very interesting work from people, I forget the exact reference, but where they make glycolysis move forwards and backwards, and I think they measure some point at which it turns, they measure the calorie concentrations, I have to look it up. But there are techniques to predict in vivo values indirectly, but that's definitely a limitation. As to your second question, if I understood correctly, the question is, are the machine learning limited to subsets of similar reactions?
Well, my guess is you're going to define a class of reactions and you're going to have some training. I mean, this learning basically means you need a training set, right? So then you're going to apply that to some new reactions. And that's going to work if somehow those new reactions are in the same general class. So,
exactly.
so that you think that that's okay. You think you know enough about how to classify sets of reactions to know what a relevant training set is for a given unknown reaction.
So I think that at least we have enough data to empirically show whether it's okay or not. I can take the database of known experimental and I can cluster them up into nearest neighbor sets, and I can do positive controls where I do know the delta G for one, and I train on one and see how well I can predict it. And based on that, but this is like a baby step. I don't think we're there yet where I can train on a more diverse set and then predict any reaction out there. And that's the challenge we want to get to eventually.
Hi, I can think of three reasons where there would be a difference between, say, an accuracy difference between what the experiment's measuring and what comes out of the models. One is that the theory doesn't apply. Another one is that the approximation breaks down whatever model you're using. And a third is numerical implementation. Can you distinguish, when you're using such a sort of blind machine learning algorithm, can you differentiate between those several things?
So, for example, when you say the theory breaks down,
That would be, the one reason is that the theory just doesn't apply. Another is that an approximation made in the theory is breaking down. And a third, which I'm particularly asking about, is like a numerical implementation. Just the way you implement it just doesn't work.
Yeah, so I think the third one is most vague and could be like a hard thing to tackle and identify. It would be like a weird box to identify. But the first two, I think we are playing around with different, for example, different thermodynamic frameworks. What I showed is typically called the rigid rotor harmonic oscillator framework. No? You minimize the structures and then you get the thermodynamics from letting them vibrate. And that's an approximation of the theory, no? But there are other theories that we are trying to test, which is molecular dynamics. You can do a molecular dynamics run, and from the autocorrelation function of the velocities, get the vibration or contribution. And so that would be some sort of test whether the theory may fix this thing or not.
So, just first, I really admire your courage to tell me you can compute these numbers with 1 kilocalorie per mole precision. Me and Zen having tried to compute that with our lives, with all these things these days, we don't believe whatever is the method we are using today is going to have this level of accuracy. The method is just not good enough. You have reactions, so that's why I want to know exactly what you're doing. You have reactions where there's major cancellations of entropy and energy with very large numbers. So to go to 1 kilocalorie. So what people have had success is not to compute absolute energies for reaction. You know a particular reaction experimentally, and then you do some multiplication of that reaction and you compute a difference between things. Are you computing difference based on some calibrated experimental numbers, or really then you're going to compute these things ab initio by mixing whatever combination of fluid mechanics and molecular dynamics?
So I'm doing differences in the sense that I'm not. You can get an experimental value for the formation energy of a molecule, and that's like an absolute quantity. I'm getting differences between formation energies of molecules, and that involves error cancellation between the methods. So if I make an error, I'm hoping that the error I make in this one is similar.
That becomes interesting in the details here, because that is actually, you have to be careful, even with your machine learning, because sometimes when you do the difference, things are additive, and sometimes they're not additive. So it's an interesting game to be played, but I wish you good luck. From my experience from Delta-G's in life, I wish you the best luck. But that's not something I would have encouraged with the current technology.
The good thing is that we have two advantages, I think, is that we're dealing with small systems. People deal with proteins. People are dealing with activation energies, proteins, etc. We're dealing with metabolites surrounded with water, and we have a database of 400 experimental.
Your same simulation, and you change slightly the size of the box of water.
I'm doing it. I'm doing it.
I'll find out. When we change the 5 kilocalories just to the size of the box. So anyway,
I'm doing it.
I'll find this work.
Last question?
I mean, this is very interesting and important, all the other comments notwithstanding. But as you know, biological systems, most of them are non-equilibrium dissipating systems where rates are key, and then force flux relationships, linear, non-linear, non-equilibrium, range. So how far do you think you could take it toward that goal, which I think is really required?
So, like I mentioned, even though the Gibbs standard Gibbs reaction energy is related to the equilibrium constant, you can, if you're out of equilibrium, and of course right now the flux going through all my glycolytic pathways inside my liver is out of equilibrium, but the standard Gibbs reaction energy is still relevant. Now I can add the standard Gibbs reaction energy of a step plus the concentrations of substrates and metabolites, and that's the Gibbs energy right now out of equilibrium in my glycolytic flux. So these quantities do lead you to non-equilibrium Gibbs energies. I read there many other complex things like rates, how you get kinetics, those are big things. I'm not dealing with that, but the thermodynamics is there.